Hello, here to talk about air and power. Air and power are unique concepts in our curriculum in that everything we do in terms of significance testing with calculations and using our calculators and things like that are about rejecting and failing to reject hypotheses. Uh, and so we never really take a strong stance in those. By failing to reject, we simply say we don't have evidence to suggest that the value, the mean, the proportion, whatever it is anything other than that, than what we've hypothesized. We aren't saying that what we hypothesized is true. Even when we reject, we aren't saying that it's something else specifically. We're just saying in general it's something else based on what our alternative hypothesis was. Air and power takes a little different look at this. And with air and power, um, there's a we look at what's called acceptance sampling, and acceptance sampling is a unique scenario where used more in the real world, but very rarely in our own calculations of where we essentially declare a winner and a loser when we develop our hypotheses. And I'll get into that a little more specifically here shortly. But the couple things to take away from this are what are type 1 and type 2 air, what is power, and how do we increase power? These are all things that um, defining these in context are very kind of popular items on the AP exam. So first of all, the idea of acceptance sampling is the notion that we really aren't singling out the null. So, and I'm just going to use an example here of height in our building again. If I say that the height in our building, the average height for all students is 67 inches tall, and somebody comes along, one of you comes along and says, no, it is greater than 67. Our students are taller. It's just because you're short that you think people are shorter, those sorts of things. And so what you might say is it's greater than 67. In fact, I think it's 68 inches. Okay, so either one of these ways could be used to portray HA in this case. We're more used to seeing just the greater than 67, but again, now we're saying we're going to have a matchup here basically between 67 and 68, and we are going to go with wherever the data takes us. Okay, so we're looking at these as really two opponents. We don't look at the null as being what we're trying to reject or fail to reject. It's not specifically to find evidence for HA like we typically have on the significance test. It's to really find evidence for which one of these is more accurate. Obviously, it's still HO and HA, and we're just introducing this alternative idea of having a winner or a loser. When we do this, we look at there's really the kind of the four scenarios here. And the four scenarios are really how these are defined up front in terms of which one is right. So this is in actuality, is the HO true? In our case, is my 67 true or is your 68 true? Okay. Now, over here, what we're seeing is the actual decision that's made from the data. Okay, so from the data, if we reject the null hypothesis, but H naught was true, then that would be considered type 1 error. Okay, so type 1 is reject HO when HO is true. Okay, now if we reject HO and HA is true, that's the correct decision there because we said that in the end my 67 is wrong. That's what the data tells us, and that's what it was supposed to tell us because it was in fact HA that was true from the beginning. Now, on the other side of it, if my claim of 67 was correct right out of the gate, and again, this word accept is something we don't use typically, but we're using in this particular case, the idea that we accept my null would be the correct decision again, because we have now said the data supported my original belief, so we do think the average height in our building is 67. By data, I mean the sample, and then when we analyze that sample, the random sample from our population. Now, if we end up accepting my 67, but the HA was true, that would be type 2 error. So type 2 error, by definition, is to reject HA when HA is true. Okay, so in this situation now, again, the new belief, your new belief of being 68 inches was correct, and we ended up going with my original belief, and so that was type 2 error. Now, when you look at type 1 and type 2, couple things to remember. HO naturally comes before HA whenever we write these, and 1 comes before 2. So if you look at this and you look at this, um, that helps you remember. And truly, a very common question that you would get on an AP exam, for instance, would be to interpret in real world context what type 1 error or what type 2 error would look like in a certain scenario. And then they'd ask you to define the consequences and things like that as well. But truly, when I see that, my original thought is, let's say it asks about type 1 error, is my mindset will start at reject HO when HO is true. So I just think of the generic definition. Okay. Now, in our example, that would be rejecting 67 when 67 is true. Okay, so if I reject 67, that means I found evidence for 68 when 67 is true. And again, I just build that up piece by piece until I have the full context of the scenario. And just as a common one with this, in our court system in our country, you are innocent as a null hypothesis and guilty as an alternative. So type 1 error here would be reject HO when HO is true. So that would be reject innocent when innocent is true. So rejecting innocent means we found somebody guilty when they're actually innocent. So now this person is in jail or has a fine or probation or whatever else. And the consequence then is they are serving some sort of punishment when they're actually innocent. Now on type 2 error, so type 2 error, again, reject HA when HA is true. That would be rejecting guilt when guilt is true. So rejecting guilt would be finding them innocent when guilty is true, or finding them innocent when they're actually guilty. Well, now somebody walks, even though they're actually guilty of the crime. And of course, that could be a danger to society or whatever that may be. So that's the sort of scenario you'll be asked to interpret type 1 or type 2 error in a certain situation, and then to discuss the consequences. And again, it could be something, there was an AP exam question about a class action lawsuit at one point. If more than 5% of a certain vehicle has a defect, then we're going to file a class action lawsuit. And in that situation, if we make a wrong decision, we may not file the lawsuit, and all of a sudden this dangerous vehicle is still out there, or we file the lawsuit and it's expensive and it turns out we were wrong, that the vehicle did not have this defect. So that's type 1, type 2 error, and again, this all comes off the heels of acceptance sampling. So what this looks like would be something like this here, where this null hypothesis, this would be my mu equals 67. The alternative would be your mu equals 68. Now keep in mind, the original decision we like to make is still based off the null, because we still entered the question thinking my 67 was correct. So this is still our original curve. Now the 68 we put in there because there was this alternative. So what happens is we still make a decision based off HO to begin with. We either reject HO, or in this case we accept it, which is this threshold right here. So for instance, if this is 0.05, as it typically is, that right away, the probability of type 1 error is going to be alpha, which again for us is typically 0.05. So that is established right out of the gate by rejecting our hypothesis. Now, of course, if this were a less than, then the HA curve would be on the other side, and not equal to makes it even a little trickier yet. But what we're looking at here is we still originally enter the problem through the null hypothesis. And so the first error that could occur would be type 1 error, which is where we have rejected the null when the null is true. And what we mean by that is, in this space right here, we might have gotten a sample that had a pretty big X bar and relative, like 67.8 inches or something. And so we looked at that and we got a p-value of 0.02 or something. And so we ended up out here. And so we said 67 is not correct. Well, again, anything under this normal curve for 67 could occur. In fact, 5% of the time, we're going to get a sample out there, even if 67 is true, right? So it's built to have this error. The only way that error wouldn't occur is if there was no overlap within these curves, and we'll get to that shortly. So what's bound to happen is we're bound to have type 1 error periodically, because if it fits under this 67 curve, we know that that's plausible. So if there's any overlap that's still under the 67 curve, that could be an area of concern, which it is right here with the type 1 error. Okay, so 5% of the time, we're going to reject the null when the null is true. So that we run 100 tests, we're expected to commit type 1 error 5% of the time if the null is true, just by where values or samples fall under the curve, because they could fall anywhere under this curve. We know most commonly they'll fall in here, but sometimes they'll be really small samples. Sometimes they'll be really big samples in terms of the X bar value. Now, type 2 error is the situation where we did not get out into that red space. Okay, so we had a sample that was still under the 67 curve, so we essentially failed to reject, right? In this case, we accepted the null, and that's this space right here where we have essentially said we didn't get out to the red space, so we're going with 67. Well, the problem is this space right here is also under the curve for 68. So in other words, if 68 is the true mean, we could get a sample in this space right here. Because again, any value under that curve is plausible. And in this case, it's clearly bigger than 5%, if that red space is 5%. And so there's even a higher probability of committing type 1 error. Now, calculating that specifically is not an extremely difficult calculation, but one that you would not be responsible for in this curriculum. And so we can determine that probability of type 2 error. And again, that type 2 error is we declared the null the winner, even though HA, or the 68 in this case, was true. And again, it's all the issue with the overlap. That overlap is the type 1 error will be established first, whatever that is, 0.05, 0.01, 0.10, whatever we say there. And then the rest of that overlap is the potential for type 2 error, which is, again, could be a value that we could get even if 68 is the mean, but we had already said that the null was the winner because we did not get out to that red space out there with our X bar value. Our X bar value ended up somewhere to the left of that line. So what we look for in these tests is power. Okay, and power is really the ability to detect HA is true when it actually is. And why power gets its own kind of special recognition is when we start on one of these problems, we are going down the road of HO. Okay, that's our current belief, and that's going to remain our belief until we show otherwise. Okay, so what we are working under this premise that we're just going to keep going straight down this road, no turns unless the data tells us to turn. And again, the data telling us to turn here would be to say, okay, we ended up rejecting HO, so we had evidence for HA, and we were able to detect that. Again, when you think about in a courtroom, the burden of proof is on the prosecution to show that somebody's guilty. And if they don't do that, we continue down this path of just presuming innocence, okay, until the evidence tells us that we have to make a turn toward guilt. And so this right here represents power, okay, detecting HA is true when it actually is. So again, you might have the question of what does power look like in this scenario? And in the court situation, power again would be detecting guilt when somebody's actually guilty. Okay, that's the HA. So detecting guilt when something's guilty, or in our example, detecting that it's actually 68 inches for the average height when it actually is. Now, power by calculation is just 1 minus type 2 error. And the reason that is if you think back to our situation of the two normal curves, okay, and we had our type 1 error here, and we had our type 2 error here, okay. Again, this was the HA and this was the HO. So this was all type 2 error. Power is the rest of this space, okay, all in here where we had HA as the winner when HA was actually true. Okay, so power really is the rest of that HA curve that's not the type 2 space, which of course is why it's 1 minus type 2 error here. Okay, so this green area would be power. Now you might get the kind of simple question of if probability of type 2 error is 7%, what's power? And you'd really just take 100% minus 7%, and so power would be 93%. Okay, and again, power is a probability of detecting that HA is true when it actually is. Naturally, as a researcher or somebody who's in a lab or is working in this space, the idea is you want to have as high a power as possible. Okay, if you need to change the mindset from the current HO mindset to a new HA mindset, you want to be able to detect that because that could change the course of the future in whatever area it is that you are in. So think about power. We want to be able to increase it as best we can. And the best way to increase power by far is to increase your sample size. And again, I will use the pictures, and I left a couple slides here to draw more, but I think I'll just try and get it down here. Is if we increase n, keep in mind the bigger n gets, the lower the variability. Okay, so if this was our HO and our HA currently, if we increase n, what we are simply doing is making these curves taller and skinnier. And if there's taller and skinnier, then there's less overlap. And when there's less overlap, there's less type 2 error. Again, type 1 error would be established still with whatever alpha is. Okay, if it's 0.05, then type 1 error would still be 0.05, but the rest of the overlap would be much smaller. So type 2 error would decrease, and if type 2 error decreases, then power increases. And again, you can kind of see it's a wheel, a collection of wheels spinning there. Of once one goes, then it affects the next, and it affects the next, and so forth. So the bigger n here decreases type 2, which increases power. Okay. The second option would be to increase alpha. And increasing alpha, again, what that is that's our typical 0.05. That's our significance level. If we increase alpha, then all we're really doing in these scenarios, and I'll even draw that one separate up here, is when we increase alpha, okay, if this was 0.05 to begin with, here, I'll make that red just to keep these consistent. If this was 0.05, and that's type 1 error, if we increase alpha, all we're doing is, if this were the type 2 error here, all we'd be doing in the situation is just covering up the blue with the red. Okay, so instead of 0.05, now this here might be 0.10, and we just have less blue space left, so that's less probability of type 2 error, which again would increase power. So again, that's the cogs of the wheel again, interacting with each other. We're increasing alpha, increase the red space, which decreased the blue space here, which meant 1 minus a smaller value for type 2 error, so power was increased. The last two here are much more difficult to attain, and are just less realistic. And the third one is to move HO and HA further apart. And that just doesn't make a ton of sense, because that would be like me saying I think the average height is 5'7", and then you coming and saying, no, I think the average height is 6'7". Okay, naturally that would move our curves further apart. We can bet that my 5'7" would win every time, even if it was 5'8", because it was between 5'7" and 6'7". So these curves would just be so far apart, okay, that there wouldn't be any overlap, and so there'd be such a small probability of error there. And then the last one, decreasing the standard deviation. Now, decreasing the standard deviation is also not realistic, because if you think about, for instance, heights in our building, we can't make the tallest people shorter and the shortest people taller so that the heights are all closer together. And there may be some scenarios in the real world where you could try and influence that, but certainly not with our heights, unless we removed students or added students to our building. Who brought our heights more around the 5'7", 5'8", 5'9", 5'10" area. And so decreasing sigma would do a lot like what we saw here, where it would just make the curve skinnier. And again, that would just be much less realistic. And so increasing n is definitely the best option there. And that's for increasing power. Again, you might get that question, how do we increase power? Or you might get the question of, what's the best combination to have the highest power? And again, the best combination, and it's typically with these first two, is the biggest n and the biggest alpha. Okay, so an n of 200 and an alpha of 0.10 is going to be better than, so if I have 200 and 0.10, that's going to be the best if it's versus 200 and 0.05, or 100 and 0.10, or 100 and 0.05. Okay, so the biggest n and the biggest alpha are going to lead to the most power, even if this 0.10 can be kind of an issue with type 1 error being pretty big there. So if your focus is power, that's how you increase it. think I'll leave it at that. Thank you for listening. As always, if you have any questions, please ask.